Okay, now we start the section 3.3, the chain rule and inverse functions. You must be familiar with this chain rule. Suppose you have a composite function like this, then when you find the derivative of the function, then you do the integration for the first function, then you do the integration for the inside function as well. Okay? So that's the chain rule that you know. So suppose you have a square root of such a function, then you do the integration for the first function first, then you find the differentiation of the inside function to multiply to get the one what you like to do. So in general, the chain rule works in this way for the composite function. You do the power rule first, then use the chain rule for the inside function. Okay. Okay. Then that makes the theorem 2 like this. Okay. Same thing. The example shows if suppose y is equal to x to the fourth minus 1 to the ninth power, then the first derivative is the 9 times x to the fourth minus 1 to the eighth power times the derivative inside, which is 4 times x cube, which makes 36 times x to the cube times the eighth power of x to the fourth minus 1. Okay, that's the way. So you know the chain rule well. So now you recall the chain rule and try to find the derivative of such a function. The composite function of exponential and the trigonometric function. Then you do the same thing. The same e to the x function times the derivative of those inside function here, which is this. So now you need to know more about these derivatives of these trigonometric functions and log functions and exponential functions and etc. Okay, here. Okay, tangent to the parametric curves. Okay, here. So this is parametric functions. Suppose you have this kind of parametric function which represents the cycloid like this. When the tire of cycle makes. Okay, this graph can be made with this parametric function. So find the equation of the tangent line which is tangent at this. Tangent which is at this point. Tangent line at this point. What you supposed to do? You need to find the derivative of this parametric function. How? How you do it? You already have learned the derivatives of the parametric functions. So now what we need is the dy dx, which can be found in this way by the chain rules that have learned. Okay, so you first find the dx dt, dx over dt, and dy over dt, and 2 makes the dy over dx. Yeah. Okay, like this, and then you have a derivative at the point t is equal to pi over 4. Then here is the derivative, and these are the point at x-axis, and this is the point at y-axis. That makes an equation like this, which turned out to be an equation like this. Okay. Next, the same problem. Find the equation of a tangent line to the curve at the given point like this. The same. You do the same thing, but only difference is you may use the sage command to find the partial derivatives of of x with respect to t and partial derivative of y with respect to t separately to draw the tangent line at the point, at the given point like this. So you may use the code, or you may change this code to deal with the other example or exercise problems. Okay, you may go there to copy this, like this. If you go inside, then you will see the copy here, which can be copied, and you may click here to do compute, paste here. Then you do evaluate, that will give you the graph that you have. Okay, that's the way that you use the code that I have developed for you. The next thing is finding higher order derivatives. Since you have since you know how to find the first derivative of a given function, so what's the another first derivative of the derivative that you have found? That's called the second derivative of the given function, which can be written as this. So this is what that means. Also, it can be written in this way too. Okay. Okay. So the higher derivative. So actually, that means in physical way, the first derivative. If the first derivative means velocity, then second derivative means acceleration of an object. Okay. Okay. In general, a second derivative is the rate of change of the rate of change. The rate of change of the rate of change. Third derivative also can be found from the second derivative, and higher order derivatives can be found in the similar way. Okay. So, for function sin x, you may try to find the nth derivative of x. Then, if you try to find the first derivative, and second derivative, and third derivative, etc., then you will see a kind of pattern to figure out the nth derivative, the shape of the nth derivative of it. And next, the position of a particle is given by equation S of t is equal to e to the minus alpha t, then times sine of omega t plus beta. Then the question is find the velocity and acceleration at time t of the function and draw the graph. Okay. In this case, you better use some tool to use it to draw the graph. And finding the first derivative is easy by using the differentiation rules. And then you make the graph. Then from this, you will see how it behaves. The velocity and acceleration can be found from the graph. So you will understand the meaning of those the functions that you have found. And Leibniz rules says, so for finding the nth derivative of the composite function, you may use this notation and choose k. Then this is called the Leibniz rule. So you may use this Leibniz rule to find the coefficient of the composite function when you find the nth derivative of the composite function. Okay. And now, this is the things. This is implicit differentiation. I believe, yes, most of you haven't worked on this implicit differentiation. So we will start from here. Okay, an explicit function can be described by expressing one variable explicitly in terms of another variables in general. Okay. This is an example of an implicit function. Okay, this is also an example of implicit function, which is the equation of a curve called the volume of Descartes. This is the function. This is a very nice and useful function, the graph, but it is represented in this way. So since we are using this type of graph, we should understand this kind of equations. In order to understand the nature of this, we need to know the rate of changes as well. Okay, so we need to know the derivatives from which is related with this type of implicit function. Okay, so this is So we studied the method of implicit differentiation. Okay, let's see. This is the one of the function, implicit function. From here, we were asked to find dy over dx. How we can do it? How? Okay. So we use a chain rule to do this process. Okay. We just differentiate both sides with respect to x. So we just differentiate this with respect to x. So 6x and dx over dx, which is 1. So we don't have to write anything here. 6xy and minus 3y square, and but here y is what? Y is a composite function. It depends on x. So here, if we wanted to differentiate y with respect to x, then we do have to differentiate y with respect to x. So we need dy dx in addition. Okay. And constant. So the other side is, and also this is the product rule should be adopted. Product rule should be adopted on here. Product. So the first term times y and times then the 3x squared times dy dx, and minus 3y y square 3y cubed square times dy dx. This is what we have. Okay. So we did use the product rule here and chain rule here. So solving dy dx from there, because we have dy dx and dy dx here, so solve all these for dy dx, which gives us this. So this is what we were looking for. This is the way. So the process is quite simple. Just use the rules, differentiation rules that we have learned. Okay, but with respect to a certain variable. In this case, it was x. Okay. Next problem says if we have this type of implicit equation, find the tangent line at the point 3 and 3. Also find the second derivative of y with respect to x at 3 and 3. So what we asked was find dy dx and d square y over dx square. That's what we were asked. What is supposed to do? Okay. So like what we did before, in order to find the first derivative of y with respect to x on this, we do differentiate both sides with respect to x. So, like, we have 3x squared plus 3y squared times dy dx is equal to this. Use the product rule on this. So, 6x times dy dx plus 6y times dx, which is 1. That gives us this. So, we solve those for dy dx to obtain this. Next step is to find the second derivative of y with respect to x. So, we do differentiate this one. Do the same thing. Here, use the quotient rule to find the derivative of this function with respect to x. All you have to worry about, the concern is just when you do differentiate y, we just use the chain rule to add. That's all. Then we can find the derivative of the slope at this point, which is -1, and the slope at the second derivative at that point here. If we want to find the tangent line at that point, then we use this slope at that point to have y is equal to -x plus 6. Orthogonal trajectory. That's this concept. The two curves are called orthogonal like this. If at each point of the intersection, their tangent line are perpendicular. Okay. For example, in physics, the lines of force in an electrostatic field are orthogonal to the lines of constant potential. In thermodynamics, the isotherms, the curve of equal temperatures, are orthogonal to the flow lines of heat. in aerodynamics, the streamlines are orthogonal trajectory of the velocity equipotential curves. So this orthogonal concept of orthogonal trajectory has many applications in physics and aerodynamics, etc. Okay, but since it just means the orthogonal, which is related to the derivatives. So all the mathematics are only using the derivatives. Let's see an example. Show that the family of curve x is equal to k times y square, and this x square plus y square over 2 equal to c, for a constant c. We show they are orthogonal. What do you have to do? Find the derivatives of the each functions and check whether they are orthogonal or not. That's it. So differentiate the first function to find dy dx and dy dx and like this, and differentiate the second function to find dy dx. Then how can you show those two slopes are orthogonal? When we multiply, if it is equal to -1, then it is orthogonal. So, as you see, y over 2x and minus 2x over y, it definitely slopes. One slope is like this, the other slope is like this. So, same value with different directions, with the different ratios. So you can easily find by just producting those two, which makes -1. That's the reason of it. If we draw the graph with this code that you can copy, and then you will see this. As you see, those trajectory and those lines are all orthogonal. You can see it in here. Example 15 here. This is what you see. So now you can check, you can visualize what I have explained. Here, as you see, those two slopes are orthogonal. Okay, you can use this, the next ones as well. And the next step is the derivative of the inverse functions. Derivative of inverse functions. Yeah, you know, if g is inverse, g is the inverse function of f, then the derivative of g is equal to 1 over the derivative of f. That's the relationship. That is the relationship. For the derivative of inverse functions, that's what we have seen. You can find the lectures on this, which is quite simple. Now, this is what you're supposed to know. Derivatives of inverse trigonometric functions. Okay. You must have seen these functions, which means sin x, y is equal to x. Okay. And then differentiate sin x is equal to y implicitly with respect to x, then you can have this one. Differentiate both sides with respect to x gives us this. From here we can find dy dx, which is 1 over cosine y. Isn't it? Okay. Then what is the cosine y? What is the cosine y? This is square root of 1 minus sine square y. Then what is the sine y, which is x? So this can be written as square root of 1 minus x square. Okay. This gives us dy dx is equal to 1 over cosine y, which is 1 over square root of 1 minus x square, which gives us this formula. Now, this is the way to get the inverse, the differentiation of an inverse function. Okay, so similarly, for the function y is equal to tangent x, inverse tangent x, then tangent y is equal to x, then differentiate the both sides with respect to x, then we have this, because derivative of tangent y is a secant square y times dy over dx. And dx, differentiation over x with respect to x is equal to 1. So dy dx can be written in this way, and secant square y can be written as 1 plus tangent square y, which is x. So this can be written as 1 over 1 plus x square. That gives us this formula. Okay? That's it. Then this is your example. So you should be able to do it. Okay? Try to do it. And so all those make this table. Okay? So yeah, we have found this one, we have found this one, and we have done the plus examples. So this is a collection of the derivatives of inverse trigonometric functions. Also, you can find all those in this. You can find all those in here. Yeah, here. These are the differentiation of inverse trigonometric functions. There are functions and arc functions, arc functions, and derivative of the functions here, and tables, and there are problems to the solutions. So there are a whole lot of things that you can use it to understand, to have a better understanding of this type of examples. Okay. Okay. Let's keep going. Yeah, before we go, yeah, we may find the errata on here. This minus sign should be in plus here for the arctangent. Okay. Next is the derivative of logarithmic function. Logarithmic function. Okay. You must have seen this equation before, high school years. Okay. So I will skip the proof of it, which is also can be done from the differentiating this equation implicitly with respect to x to get this, which gives us this. Okay, it's the same thing. So it's all these can be obtained by the implicit differentiation. Okay, as a special case, if we put a is equal to e, then we have this. So that's why the derivative of ln of x is equal to 1 over x. Okay, so yeah, now you should understand the power of the implicit differentiation. Okay? Okay. And for the composite function, yeah, you can generalize it. So, suppose we have the example like this to find the first derivative of it, then we do the two different integration, either differentiation to the separate derivatives on each intervals. Okay, and differentiate the okay. And there are several examples of the implicit differentiation for logarithmic functions. Same thing here. Here you do what we did. Here we take a log function on both sides and then take the differentiation on both sides with respect to x to get it to find the dy dx in this way. So it has a whole lot of applications. Okay, if we have an implicit equation like this to find the y prime in terms of x and y, then take a logarithm on both sides, differentiate implicitly on both sides to find dy dx in terms of x and y, like this. Okay, this is the way. Okay, here's one remark. From the definition of a derivative of logarithmic function for f of x equal ln of x, here we can find the limit of this. So now for the function f of x equal ln of x, the f prime of 1 is this from the definition. So when you see this type of the function or limit, then you should be able to find the relationship with the log functions. From there you can even think the exponential function like this. So exponential function e can be written as this. The 1 is a limit of this function. So the limit can be moved from here to here because they are all continuous function. This value can be, since this e to the ln of this function is e can be cancelled, so it can be written in this way. So this is this. 자, 아까 this gives us this formula. E is equal to the limit of these functions. And also, also E has a lots of meaning. I have told. It's a summation of a special series and limit of this. And if we replace this x by 1 over n, then the E can be written as a limit of 1 plus 1 over x to the nth power as n approaches to infinity. Next, hyperbolic function. Hyperbolic function. You must have seen this kind of the shape before. This is a kind of hanging wire. Yeah, when you go through on the 전봇대가 있으면 이 라인 전봇대에 걸린 전신주에 걸린 전기줄들의 모양이 이렇죠. This is called the catenary curve. 이 전봇대, 그다음에 이 전선. Okay. This catenary curve can be written in this, with this hyperbolic cosine. Okay. This catena means chain in Latin word. Okay. So this kind of nature is what we often see in around. So we should, in order to understand the nature of this, we should know, we should have some knowledge on the hyperbolic functions, like this. First, hyperbolic sign is defined from the e to the x. Hyperbolic cosine also defined with the exponential function like this. From this, the combination of those two functions makes us a hyperbolic tangent like this. Hyperbolic cotangent, which is the opposite of reciprocal of it, and hyperbolic secant, hyperbolic cosecant like this. So if you know these two, then all others will be followed. So this is all you know. Sine, hyperbolic sine is minus sign here. Hyperbolic cosine has a plus addition over 2. Okay? That's what you know. Then all others will be followed. The graph of the hyperbolic functions, hyperbolic sine, hyperbolic cosine, hyperbolic tangent, hyperbolic cosecant, hyperbolic secant, hyperbolic cotangent, like this. And from the given relationship, we can draw so many equations like this, like this, like this, and also we can draw many things. You can draw many interesting relationships related to the hyperbolic functions. Okay, so from those simple equations, we have drawn a lot of interesting equations. With the implicit differentiation, we can easily draw the derivative of hyperbolic functions like this. So this is all can be found from the definition. And some techniques on differential rules. So let's find the differentiation or let's differentiate the hyperbolic sign of x squared. Then d of dx make us this implicit differentiation. The chain rule gives us 2x hyperbolic cosine x squared like this. The same thing for the log. All you have to do is just use the rules with the table. I will, if I ask you to do, I will allow you to use those tables because you don't have to just reproduce all those or memorize all those formula in your hand because those are the things that you can always find. And also, you can easily find from the website for those tables. But what's important is you should be able to use those tables or those internet informations to solve your own problems. That is the real things. So I expect you will be able to utilize all those resources and tables and informations to solve the problems that you will face. Okay. Okay, simply on the sage, if you give the simple the command like diff, then it will give you the differentiation of all those hyperbolic functions as well, inverse hyperbolic as well. So here is the inverse hyperbolic function. So now, before we studied the hyperbolic function and derivatives of a hyperbolic function. Now we define inverse hyperbolic function and the derivatives of inverse hyperbolic functions. Okay, here let's think about the inverse hyperbolic tangent function like this. Then this is equivalent to x is equal to hyperbolic tangent y. Right? So x so 여기 hyperbolic 빠졌네. 좀 고쳐주세요. So here x is equal hyperbolic tangent y, which is this. Then this can be written in this way. So from here, yeah, we can write y is equal to 1/2 of ln of 1 plus x over 1 minus x. Also, we can draw the all inverse hyperbolic functions in this way with using the graphing tools. And this is the from those simplification the inverse hyperbolic function can be written in this way. And the derivatives of the inverse hyperbolic function can be found in this way with the techniques that we have developed so far. Okay. And the differentiation of those can be found by using those the tables or what? Computational tools now. So you don't have to bring all those big tables to deal with it. Now you can use a simple computational tool to deal with it. For the informations, you can use your website to get the details or tables on it. Okay, now here is the examples. Find the differentials, dy, or find the derivatives of these functions. So I expect you may try this by hand or any of the computational tool which is available. I think that it wraps up the chapter, section 3.4 to deal with it. And now we close up the section 3.3. There are, as you see, there are many interesting but complicated ones there that you can handle by hand or with the computational tools. Next time we will finish up chapter 3 with the approximation and related rates. Okay, any questions so far? Okay, then class dismissed.